Okay, hello guys, and welcome to the second video of the second chapter. In the last video, we talked about variables and data types. So in the end, we talked about how we can store data in like a digital system, like a computer. And today, we will talk about how we can actually perform operation on this data, right? So previously, I told you that computer science is all about representing data in any way. And when we talk about data structures in more detail, you'll understand that there are many different ways you can represent the data. But for now, we can see that this is an oversimplification, obviously, because we don't only want to represent data, we want to manipulate data, we want to perform operations on data, we want to do something with the data, right? So without further ado, I will talk now about operators, and maybe by extension a little bit about functions, but we will talk about functions in depth, even on the beginner learning level, in the next video. Okay. For now, I want to give you a useful abstraction. I think it's a useful abstraction. And this is what I call the black box model. Okay. Or you could also simply call it a box model in the end. It doesn't matter, right? First, I'll draw it, and then I'll explain it. Think about this box as being an operation. Okay. So a very simple example would be a trivial example indeed, which would be addition, right? Think about what this little arrow right here as representing the input to this operation. And think about this arrow right here, or maybe, yeah, as representing the output of that operation. So in the end, this little picture right here is a way of representing the behavior of an operation. Of course, there can be multiple inputs. For example, you know that addition is what we call a binary operator, yeah, because it takes in two values, right? We add, for example, two values. So yeah, this is like the abstraction I want to give you because it's very useful when talking about the different types of operators there are. I think this abstraction, this a metaphor in a way will get more clear as we move on, because we firstly have to distinguish between different types of operators. Yeah, I'll simply write it down and then I'll explain. They are the arithmetic operators. They are the what I call the logical arithmetical operators, and then there are simply the logical operators we know from logic. We may know, but I will talk about them in detail further on. So let's think about the arithmetic operators. These are simply operation on numbers, of course. We know we can represent numbers as, for example, whole numbers as integers or doubles, right? So if we think about arithmetic operators in the concept of like computer science, we can simply represent these operators by this box. All of these operators are, in a sense, binary operators, almost all of them. I'll talk about this later as well. Wait. The thing is, a part of my skin gets cut off, so that's pretty annoying. So I'll try to think about this. But let's think back to what I call arithmetic operators. They take as input the binary arithmetic operators. They take it as an input numbers. So the input is numbers. Of course, you could also talk about integers and doubles, but for now, let's simply call them numbers. And the output is also a number. Okay, very simple. We know these operations. For example, it's addition, subtraction, multiplication, division. Let's symbolize the division that way. Of course, there are more exotic operators, for example, the modulo operator, which is pretty important in computer science, and I'll talk about this operator more, and there will be many practice projects where you have to use the modulo operator. But for now, simply realize that on one level of abstraction, they are actually the same, right? Because you add two numbers, and as a result, you get a number. You subtract two numbers, and as a result, you get a number. All these operations take as input numbers, and and the output is the result of that operation. And it's also a number, necessarily so. Okay, so maybe let's think about this little black box model again. I call this input, this is the operation, and I call this output. You could also, in this context, simply say the result of operation. Okay, just to be crystal clear. Once more, I forgot. Man, this is really bothering me, so 1 second. So I'm back, sorry for that. I now resize the window, now there are this edge to the window, but it doesn't matter. So just to be crystal clear, I once again gave you this abstract way of thinking about stuff. And this is all there is to arithmetic operators. Arithmetic operators are on numbers. They are binary operators, and they, as a result, as an outcome, they always have numbers. You might ask yourself, okay, but what about a case like 1 plus 2 plus 3? Okay, isn't this like not a binary operator because we're adding 3 numbers? And obviously it isn't in a way, and I should stop saying obviously because it's didactically not that good. But if you want to compute this sum, you always have to compute it in a binary rate. For example, you could say, first I'll add these numbers. Okay, the outcome is 3. So this expression reduces to a 3, then the remaining 3, I'll simply add to it, and I'll get a 6, okay? And even for more complicated operations, for example, if I say 1 plus 3 times 4 plus 2 or something, it's a binary operation. It's a like are multiple binary operations, and in the end you get a result. Okay, so these brackets always indicate the precedence, right? We know this from mathematics, but of course, you could also distribute the multiplication over these brackets. But for now, we won't do that. We can simply say, okay, 1 plus 3 times 6. We can now simply skip this. We know that the multiplication takes precedence over the addition. Okay, so we know this is 18. So these are all binary operations, right? So in the end, there's 19. Okay. Yeah, should be pretty obvious. I just talked about this because to make sure you understand that these even more complicated like formulae can be translated into just a set of binary operations in a certain precedence and order, right? Yeah. So let's get rid of this and let's talk about the logical arithmetical operators. And of course, this is a very fancy like name, but the concept behind it is actually very, very simple. And this is only to give you a rough overview, right? Okay. So once again, let's think about logical arithmetical operators, or LAOs for now. These are simple arithmetic operators. Okay, maybe let's give them a different color. So these are AO. This is a LAO, or logical arithmetical operator. And now something interesting happens. These also have like as input numbers. So these are also numbers, operators which take as binary operators which take as input numbers, but they actually have a boolean, a truth value. So either true or false, as an output, as the result of the operation. Okay. So remember, a truth value is simply it's either true or false. This is what a truth value is. Okay, it should be pretty obvious, right? And we can, for example, less than. Okay. I can ask myself the question, and this, of course, these are very trivial examples, but just to make it more concrete, I could ask myself, is 2 less than 3? And this maps to true, right? So I'll put 2 and 3 into this little box, then the magic happens right here. The magic meaning the simple logical operation, the simple logical arithmetical operation, and in the end it gets mapped into a boolean, a truth value, true or false, right? In programming, because these are like a mixed case between an arithmetical operator and a logical operator, this is why I chose that name, right? But in programming, there are even more like logical arithmetical operators. For example, you can check for identity, but these are not strictly arithmetical because you can check for identity even in strings, okay? So let's talk about operators in computer science or in Java to be more precise, which are particular to computer science when we get there. But for now, just realize there's smaller than, there is obviously bigger than, and these are in the strict sense, and there's smaller equal, bigger or equal, right? So yeah, this should sound familiar to you. This is what we learned in high school, and even before that, right? So now the last category of logical of operators I'll talk about are the logical operators. Okay, and these are also very interesting. Once again, let's represent it in that way. And in a sense, they're very similar to the arithmetical operators, but they don't take in this because their input is from the same data type, so to speak. As an input, they have booleans, so truth values. Okay, this is the equivalent way of talking, but they also output a boolean. Okay, also output a boolean, a simple truth value. And you may not be too familiar with these logical operators, which is why I will talk about them a little bit more in depth. But for example, think about AND, okay? Let's think about what happens. For example, let's give you a sentence, okay? Let's give you 2 sentences which make it a little bit more concrete and which, yeah, simply elucidate maybe a little bit further what I'm talking about here. So let's take a statement like A, the sun, I'm sorry for my handwriting, the sun is at the center of our solar system. And let's take a different proposition, okay, or sentence. There's a video on this channel where I talk about propositions. Maybe I'll link it, maybe I don't. So we know this is obviously true, right? And now let's think about the statement which isn't true. And of course, there are infinitely many false statements. But for now, let's say Donald. What is happening here again? 1 second. Donald Trump is president. Okay. Thankfully, this isn't the case. President of the United States. Okay, this should be pretty clear. And yeah, this is obviously false. Okay? And now let's think about what happens when we combine these 2 statements with an AND, with a logical AND. We say A and B. Okay? If, for example, imagine this in a discursive setting. Someone says the sun is at the center of our solar system. Okay, there's nothing you could argue about that. That's simply true, right? And then he says, and Donald Trump is president. Now he stated something wrong, because if you combine a true statement with a false statement using conjunction, the conjunction is false, because the conjunction is more strict than the logical or. Let's think about the statement A or B, okay? The sun is at the center of our solar system, or Donald Trump is president. This stays true, because A is true, B is false, but the logical or is, in a sense, less strict than the logical and, because this also evaluates to true. And this should be pretty obvious to you, because we have these logical intuitions, and in a sense, this is maybe just this is just a way of introducing stuff, because what we are talking about here in a very informal way is what we call propositional logic, where we can actually talk about the content of sentences. And of course, in informatics we don't do this. It's in the end we don't think about true or false propositions. We think about it in a more abstract way. But you can realize that this little thing right here, which maybe I should have stated this explicitly, is simply, for now you can think about this as representing or, and this as representing and. And I know the little whiteboard here gets a little bit too much, so I'll delete it and I'll erase it in just a second. But these are also operations. So we send in A and B, and we get a true or a false value. Okay, so maybe let's think about this stuff a little bit more in depth, and maybe let's clean up this messy board, because logic is very important in computer science. In a way, logic is the foundations of computer science. But yeah, okay, let's draw our favorite little picture again. Once again, Boolean input, some logical operation, I abbreviate it with L, and the output, the outcome of that operation is necessarily also Boolean, because we're talking about logical operators, right? And now I'll give you the most simple logical operator there is, maybe to simply get started, right? And this is the negation. So let's first start talking about the negation. In logic, we symbolize it with this little symbol right here. In computer science, for example, in Java, not in Java, in Python, we write something like, we can write something like not. And in Java, we write the simple exclamation mark. So this is Java, Python, I call this formal logic. Okay. And I studied logic in college. I mean, so I could get into way more detail here, and I will upload many more videos about logic on the intermediate and advanced learning level. But for now, this shall suffice, right? And negation is actually an example of a unary operator. So this is a unary operator because it takes in only one input. Okay, and this is pretty easy. It takes a Boolean as an input, and it takes a Boolean as an output, and it simply flips the truth value. So true becomes false, and false becomes true. This is how negation works. It should be pretty obvious to you. And of course, this abstraction is pretty useful, and I like it very much. And I'll use it when we'll talk about functions as well. But there's a better way of actually representing these logical operators. There are what is called truth tables. Okay, and think about these truth tables as defining these operations. Okay, let's give you the most simple truth table is. Let's say A. We simply write Boolean A, so we know A is a truth value, and now we can think about every possible combination. And of course, in the case of a single variable, it's very easy. It's either true, false, or true. This is by the law of the excluded middle, so yeah, okay, I don't have to get into that. And the operation can simply be defined like this. Of course, and this is an absolutely fine definition. It's also a very general definition, because from this we can also conclude what this statement, maybe we should make the brackets right here, evaluate state. Because we firstly evaluate this, let's say A is true, for now, suppose A is true, so this becomes false, and negating it again, that's true. Becomes 1 again, right? So this is obvious. So just again, I wanted to show you that it doesn't matter how many times we actually do this operation, because it can be defined in this like simple way. Okay. Of course, there are other operations we already talked about. 1 second, I'm having problems again. Am I still recording? Am I still recording? Yes. Okay, so bear with me. This is really annoying. All these technical difficulties I'm encountering. So this is the negation. So we talked about negation. And maybe now let's look at the binary logical operators, and there is AND, okay? And of course there are fine distinctions here, okay? The way we use AND in natural language is not the same as the logical AND, because the logical AND is simply a part of a formal language called propositional logic or predicate logic. But I'll just brush over these differences for now, right? We know the AND, we know how OR works. There is yeah, okay, let's talk about them for now, okay? And since they are binary logical operators, they take as input 2 values, okay? And now let's think about every possible combination of these truth values, okay? So both could be either false or true, or one of them can be false and the other true, or the other way around. And I'll symbolize AND with this little symbol right here. This is custom in logic, and OR by this little symbol right here. And then now let's think about A and B. Okay. And maybe let's just write the truth values from A underneath A right here, so it's easier. 0, 1, 0, 1, 1, 0, 0, 1, 1, 0. Confused myself there a little bit. And if we want to define how this logic operation right here works, we simply ask ourselves if A and B, and now it's a little bit funny because I'm talking in a meta language like about logic, so the sentences I'm uttering now may sound a little bit weird to you, but if A and B are false, B is also false. A and B is also false, right? So this is false. If both of them are true, A and B is true. Well, very obvious. But, and this is why I told you that the logical AND is in a way stricter than the logical OR, I'll talk about it in a few seconds, because if one of them, if either A or B is false, the conjunction also becomes false. We can call this conjunction, it's a fancy name for just an AND connection or between two booleans, right? So this is also false. Let's think about, and this is a very rushed introduction into truth tables. If you want to like further expand your knowledge on this topic, maybe upload some more videos. But I'm actually not a big fan of these truth tables because they're a bit tedious. But there are many resources on YouTube, so you can just go ahead and watch those if you would like to. So let's think about A or B. Once again, just to be clear, let's write the truth values we specified right here down here, so it becomes a little bit easier for us. And of course, A or B, if both of them are false, A or B is still false, right? So this is still false. This is true, but this is the important distinction between the operation of logical OR, we call this disjunction, and the conjunction, because if one of them, what is happening again? Man, this is annoying. Because if one of them is true, the disjunction is actually also true. So in this sense, the logical OR is less strict. Okay? And the interesting thing, just by using negation and disjunction, or or using negation and conjunction, or by simply, you can actually define every logical operator with one simple operator, which is called the Sheffer stroke. I think, don't quote me on that, you can Google it, but for now, let's think about it. You can define any logical operator you want. So in a sense, logic is very simple in that way. So yeah, we can also prove some equivalences simply by using truth tables, and then I'll promise you to stop talking about logic, right? Because maybe it's a little bit too much. But for example, there's De Morgan's law, which states, this is one of De Morgan's laws actually, that not A and B is equivalent. And here we are also, you see, this all comes together right now. We're also using operator, but this is like a meta operator in a meta language, because we're talking about formulae now, logical formulae. But this is simply equivalent to not A or not B. Okay, this doesn't seem too obvious maybe for you, but we can prove this using a truth table. Okay, and there I can also show you how like these operations like negation and conjunction can actually be combined. Let's think about not A, and this bracket right here is very important because the negation takes precedence over the conjunction, so you have to write these brackets right here, not A and B. Let's simply write down these truth values again, because I did this a lot in college, and if you are familiar with this stuff, you can do it without writing it down, but I think didactically it's more useful if we for now just write it down, right? And now we have to evaluate this and of course both of them are false, true, false, false. You can look it up right here, right? That's the same. And now we have to flip these, because we still have to negate it, don't forget about that. So it becomes 1, 0, 1, 1. So this is our result. Yeah. And once again, maybe I should be more clear. These are all possible truth values in the case of A and B, right? Of course, this could be more complex. You can have like n propositional or Boolean variables right here, but for now we stick that with the special case of 2, because as I showed you, in the end, these are binary operators, and more complex formulae are simply successions of applications of binary operators, okay? And this is what we call in philosophy a definition of truth functionality of logical operators. Okay, but this is just an aside. This may be a little bit too verbose for you to abstract. This is okay, you can forget about it in the end. But okay, now let's think about, because we still have to evaluate this right here. So it's not A or not B. Remember, I told you that like the negation takes precedence over these other operators. So A, 0, 1, 0, 1, 1, 0, 1, 1, 0 right here. Remember, we still have to evaluate the negation, so we simply flip it. So this becomes a 1, this is 0, this is a 1, this is 0, this is a 1, 0, 0, 1. And now we look at the final operation, binary operation you have to do, the logical OR. True, all true is true, false or false is false, false, true, true. And now, maybe I should have written this in yellow, because I wrote it in yellow here as well. So this is a 1, a 0, a 1, and a 1. And now compare these two columns, so to speak, and they are totally the same. And this proves the equivalence. Because think about it, these are all the possible truth values in the case of two variables, and we demonstrated that for every possible combination, these map to the same truth value. Okay? So this was a very quick and early introduction into like logic in general. And you may ask yourself, why do we talk about logic? Why logic? Okay? And this is very important because there's an interesting mapping, as I already told you in the last video, between the binary system, and simple on-off signals. Okay? Obviously, you can simply say, this is a way of modeling information. You can simply say, okay, every time there is like, okay, let's imagine a simple electrical like wire, so to say. Okay, I'm not an electrician in any way, so I may use weird words when talking about it, but there can either be power on, okay, or there is no power on, right? And this can be represented, and actually is represented in your computer, using binary. We can simply say, okay, whenever there is like electricity flowing through this little wire right here, we represent this as a 1. And if there's no electricity flowing through this little wire right here, we represent this by 0. Okay? And this is how actually, for example, okay, this is a very quick introduction on how this stuff will work. I will upload more videos in the future. So let's say this is your CPU. And your CPU is like, it's a very nice metaphor actually, the brain of your computer, of your PC, right? Your personal computer. And now let's say let's say this represents memory, okay? And at a certain address, at a certain location in memory, we stored a value like, for example, 3, okay? And remember what I told you like in the last video, 3 is simply stored as this. Okay, of course, let's say we have like this location is actually 4 bits of size, so it would be stored like this. Now the CPU reads this value into a register, which you can think is like a very quick type of memory, which is the type of memory that CPU can actually access very quickly. And what comes back into the CPU is a simple stream of on-off signals. Okay, so you can imagine it like this little wire. Of course, it's more complicated than that, right? But in the end, it's like off. So the CPU knows this is a 4-bit number. Off, off, on, on. So there's no electricity, electricity flowing, and this is how this number is actually stored in memory, right? So in the end, what the CPU is actually executing, is actually decoding, is a stream of binary data represented via on-off signals, in which we can think about more abstractly in the binary system, right? But okay, this is like a more like elaboration on what I talked about previously. But now there is something called logical gates. Okay, I have to admit I'm not an expert on logical gates, but these are analogies. Or what do I mean analogies? By using logical gates, we can actually model the same the logical operations we talked about earlier, and we model it in a physical system, okay, in a computer. And this is why logical operations are so foundational to computation, computation of course, but also computer science, because let's say we want to represent how the logical end functions in the end, okay? So let's say there are 2 wires now, okay, going into this little box, which is our gate. And now it comes out, and we can, and we already know how this AND gate, okay, let's say this is an AND gate, works. Because if I demonstrated the truth table previously, so I'll imagine you already know how this goes, right? If both of these wires are actually, there's actually a signal, so some electricity flowing through them, the AND gate will output an on signal, okay? In any other case, it doesn't. And this is like modeling the truth table we talked about earlier, just in a physical system. And this is actually like the basics of how we can teach, in quotation marks, the computer and how to do like logical operations on data. So this is should motivate why I talked about logic that much. Of course, these topics are way more complicated than I talk about for now, because we're still at the beginner learning level. But this should be pretty clear right now. Yeah. So let's talk about operators now in programming. And then I promise you we'll actually start coding, but I just wanted to lay the foundations, right? Because I think it's very important in general. This is something I really truly believe. It's very important to have like a good grasp on these abstract principles of like let's say mathematics or computer science. So I'm very like into first principles thinking and stuff like that, or having a good abstract picture of what's going on. Whew, okay. Of course, operators in programming work a little bit differently than in logic, or let's talk about computer science now, than in logic or mathematics, because these are like, mathematics and logic are formal languages, okay? These are obviously not computers. So in computer science, for example, in mathematics, we simply know, okay, let's draw this little box again. Let's say this is the addition operator. Okay, we know, okay, this comes from nums, and this maps into nums, okay? Input nums, output nums. So this should be pretty obviously. But in computer science, this simply isn't the case because we have more data types. Think about math as being the field of inquiry where there's only one data type, namely numbers, okay? But in computer science, there are many data types there. As I told you before, there are characters, there are strings, and so on. So the only requirement we have, for example, let's say we talk about the plus operator, okay, is that these 2 things are of the same data type. The same data type? And of course, you can restrict this. So for example, it makes... yeah, okay, let's not get into too much detail now. Okay, so let's say we put in an integer there, and then integer there, and since if you add 2 whole numbers, you only get a whole number, this will map into the integers, right? You can also use doubles right here, right? Stuff like that. Doesn't matter. But, and this is the important part, you could also use strings. But then, in a strict sense, we talk about a different operation, okay? So even though this is a little symbol right here, we write it in Java, for example, when we say a plus b, if we declared these variables beforehand, right? And let's say with ab integers, right? But there's also a plus b with ab being strings. And this performs the operation of concatenation. I'll show you right in a few seconds. But in a strict sense, these 2 operations, although they are symbolized in the same way, are pretty different, right? Because they have like a different input-output structure. If we put into this operation an integer, 2 integers as an input, we get an integer. But if we input strings, we get a string, right? So in a strict sense, these 2 operations are not the same, and this should be called, and I think this is actually called operator overloading. If you come from like, if you already have some programming experience, you know, there's actually, for example, if you define your own class, you can actually overload this operator as to do stuff for your specific like use case and class. But I just wanted to show you that in computer science, these operators are a little bit more complicated because we're talking about different data types, right? The possibility of inputting different data types. So for example, let's give you an example. So 2 plus 3, if we, like, let's say this is now in our Java code. Let's say z equals 2 plus 3, and we print z. Of course, there should have to write more, but I don't want to write it out right now. This simply outputs 5, right? Simple addition, we talked about this earlier. But if we now say, okay, this is a string as indicated by these double quotes, you should know this by now. And let's say there's a different string, and now we add them, right? So we put them into that little box. we get as an output hello world. So these two strings just get concatenated in the sense that this will be put right after the first string. Okay. And now if you would like, and this is obviously nonsense, but if you would declare some, if you would do this, you obviously don't get 12, and you don't get 3, I mean, you get 12. Because now we are not using integers as input to that little operator right here, we're using strings. And for this, so you could indicate this by this little subscripted s, is simple string concatenation. So this is just something I wanted to tell you like in general, so we are clear on this. And yes, in the next video, we'll finally start coding, and this way of presenting this topic has the benefit that you are, when we start coding, actually already familiar with like these different types of operators and this, I think, useful abstract model, like this black box model of thinking about operators. So see you in the next video. Bye bye.